entropy and the basic form of the spectrum, and given Wilson's definition of what a quantum field theory is, it almost tells you that asymptotically anti-de Sitter quantum gravity is a conformal field theory in d-1 dimensions. So now apply this principle to asymptotically flat space-time, thinking about a time-like generator of the Poincare group as the energy operator. Then the density of states that's implied by this goes like the exponential of the energy to the d-1 over d-2 over d-3 power in d space-time dimensions. And that radius is always growing up faster than an exponential of the energy. So the consequence, the kinds of things we like to think about in quantum mechanics, the correlation function of operators at fixed time in the vacuum state, are not distributions on a space of functions with compact support. In plain language, that means you can't really talk about operators at fixed time. You have to smear them out in some way with a particular exponential fall-off in time that depends on what dimension you're in, and is determined by the black hole energy spectrum. Now, one way of looking at this is to say, oh yes, we think about Minkowski space as we do anti-de Sitter space, think about the conformal boundary. The theory that we might want to define lives on sky plus and sky minus. And if I do that, I can see there's no Hamiltonian version of the theory. There's no time evolution that you can define that makes any sense on sky plus and sky minus. You can see this just by thinking about the theory of massless particles described on sky plus and sky minus. The equations of motion are already solved. But there is another way to approach the dynamics of quantum mechanics in an asymptotically flat space-time, namely light cone physics. And in light cone physics, the Hamiltonian is T minus, sorry for being old-fashioned. It's like m squared over T plus, where m is the mass. And that means that the spectrum as a function of T minus is better behaved. You get an extra factor of a half in the exponent as a function of T minus. There's a 2 in the denominator in this formula here. And as a consequence of that, for every non-compact dimension greater than 4, light cone quantum mechanics behaves as we've always imagined quantum mechanics to behave, and has what might be a reasonable set of correlation functions at fixed light cone time, and we can imagine trying to do the conventional sorts of things that we do in quantum mechanics. And indeed, there are some models, the matrix theory versions, admittedly not really in asymptotically flat space-time, but only with discrete light cone quantization, that seem to describe things, but only in light cone time. By the way, I'd like to point out that d equals 4 is special from this point of view. In d equals 4, suddenly even the light cone Hamiltonian has a spectrum that grows exponentially with the energy. That's Hagedorn behavior, and not like the Hagedorn behavior of strings, which is exponential in the time-like generator, but the Hagedorn behavior in T minus. So even light cone Hamiltonian physics might not be well defined. And I believe that this pathology is probably connected with other things we know are wrong with four-dimensional space-time, namely the problem of infrared divergences, the non-existence of the S matrix, the fact that consequently you have to work with the Bondi Sachs group rather than the Poincare group, and so on and so forth. It's 4 dimensions is going to be more complicated than any other dimension. And we're stuck. We happen to live in 4, so we're going to have to understand it. One final remark I'd like to make here is that even in quantum field theory, when I work in the light cones, a change of vacuum state is always implemented by changing the Hamiltonian. Now, in field theory, we think of this as a defect of light cone physics. But I want to suggest to you that given the context of these other ideas, that may be, again, another hint that what we've got is, in general, different Hamiltonians rather than different states of the same theory. So now let me come back to this other method of finding one vacuum inside another. Maybe there's still a way we couldn't do it by going and looking at the high energy behavior. What about forming bubbles? I dealt with this paper that I wrote a little while ago, and the bottom line is it doesn't work. If you try to make a bubble, and you have some tension when you do this, always in the bubble wall, it costs you some energy to make this because in order to change from one vacuum to the other, you have to pay something in the bubble wall. And if that's the case, the mass of the bubble grows like the radius to the d-2 dimensions in the space-time dimension. And so the Schwarzschild radius of the bubble inevitably gets larger than the bubble size. And so you can't make, in principle, bubbles of arbitrarily large size in the theory of quantum gravity. And if the tension, the barrier between domain walls, is aboard a Planck scale, this maximal size for bubbles is aboard a Planck scale. And so it really doesn't make sense at all generically to think about bubbles. You can only think of them as asymptotic quantities, asymptotic things that might make sense in certain regions of moduli space. You might imagine that that allows you to connect different disconnected moduli spaces by sort of going down to extreme regions and connecting them together, as we saw in Shami Petra's talk. But in fact, you're defeated because even along the moduli space, it turns out, that although you can make bubbles of a second vacuum inside the first one, you have to do it in a very, very intricate way, in such a way that if the distance in moduli space between the two vacua is d, then the size of the largest bubble you have to make in order to see vacuum number 1 inside of vacuum number 2 is exponentially growing with the distance in moduli space between. And so there really is no way to get around this by going to extreme regions of moduli space. Now, the reason that bubbles exist in quantum field theory It's really because in any quantum field theory, supersymmetric or not, if I make a big enough bubble so that it's exactly flat, and the limit of its radius goes to infinity, it's a domain wall, and every time I have discretely separated vacua, there are topologically stable domain walls in quantum field theory. So another way of investigating these problems that I'm talking about is trying to think about the cases that we know about in